Hi folks, this is number 20 from page 420. So they give us three vectors. Now they were given using the standard basis vectors, but I find it much easier to just work with them in component form. But certainly you can work with it using the standard basis vectors. So here's our three vectors, and they want us to determine a whole bunch of operations. Okay, so the first one, nice and easy, just a cross product. Okay, so I'll set this up with my two vectors, one over the other. So 1, -2, 1, and 2, -1, 1, and I'll bring over my x components to the other side. Okay, and so P cross Q is just going to be equal to, so what do we have here? So y and z components for x, so -2 minus -1, so -2 plus 1 is -1. Here we have 2 minus 1 is 1, and here we have -1 minus -4, so -1 plus 4 is 3. Okay, and so here is our first answer for A. For B, they want us to determine this cross product for, so P minus Q cross P plus Q. So a couple of ways you can do this. So one way is to just do it directly, which is find P minus Q, find P plus Q, take the cross product, just grind it out. The other way, I guess, would be to actually distribute this cross product, because in the end, I'm going to end up with P cross P, which is just 0, Q cross Q, which is just 0, and I'm just going to end up with a couple of P cross Qs and Q cross Ps, and I've already found that cross product. Okay, so let me do it both ways just to show you that it does work. So if I just grind it out here, let's do P minus Q, so 1 minus 2 is -1, -2 plus 1 is -1. And then here we've got, where is it? 1 minus 1 is 0. Bring over the -1. Then let's do P plus Q. So 1 plus 2 is 3. -2 minus 1 is -3. And then here we have 1 plus 1 is 2. Okay, bring over the 3. And let's see what that gives us. Okay, so it gives us -2 minus 0, so just -2. Here we've got 0 minus -2, so it's going to be plus 2. And then here we've got 3 minus -3, so 3 plus 3 is 6. Okay, and there's our answer. Not too bad. But let's try it the other way. Let's actually multiply, let's actually distribute this out. Okay, so we end up with P cross P plus, do that one there, P cross Q. Okay, then here we've got minus Q cross P. And here we've got minus Q cross Q. Okay, so just ignore that phone ringing if you can. So here, this is just equal to 0. That's just equal to 0. So I've got P cross Q. And here, this is minus, and remember, these two are not commutative, they're anti-commutative, so that's just going to be equal to negative P cross Q. And so what we have in the end is 2P cross Q. Okay, and since we already found P cross Q, that's just going to give us -2, 2, and 6, which is exactly what we found before. Okay, so two ways to attack this problem. Okay, now part C, again, I could grind this out, but I really think there's a much easier way to do that, because what does P cross R give you? P cross R, okay, is just perpendicular to both P and R. Okay, that's how we defined this cross product. But if it's perpendicular to R, then that means the dot product here has to be equal to 0. So P cross R dotted with R has to be equal to 0, because this vector by definition is perpendicular to R here. Okay, so there we go. And again, if you did grind it out, you did everything correctly, you should get 0. Okay, and the last one here, well, this one I can't really see a fancy way of doing it. So we already have P cross Q, so that's -1, 1, 3. And we have R, which is 0, 1, -2. And so let's find the cross product here. So we have -2 minus 3, which is -5. And here, oh, forgot to carry those over. 3 times 0 is 0, minus 2 is -2. And then here we've got -1 minus 0, so just -1. Okay. So I guess to recap here, first of all, usually much easier to work with these vectors in component form instead of standard basis form. And here, there's a couple of them where we were able to use properties of our vectors in order to solve it in different ways. Otherwise, you could just grind all these out. Okay, that's it for this.